In this video, we'll look at selection bias or omitted variables bias, and we'll also talk about the sort of special case where our regression estimates might have a causal interpretation. So here's a simple regression model you're familiar with, and an important point to make up front is that our slope estimate is just based on a comparison, right? We're just fitting a best fit line through our XY scatter plot. And so we're essentially asking what beta 1 hat is giving us an answer to is, how does y tend to change when x changes? Okay, it's just a correlational device, this regression. In general, the answer to this probably reflects maybe some causal effect of x on y, but also other reasons why x and y are associated, okay, which here we'll call selection bias. All right, this refers to the idea that different values of the explanatory variable, observations with different values of x, differ in other ways too. This is called selection bias or omitted variables bias, because the idea of an omitted variable is there's something that's in the error term in the simple regression, okay, that is correlated with the x variable. Let's do an example here. So on the next slide, we'll come back to that first slide in just a moment, but on the next slide, these are examples of causal questions. These are questions in applied economics where we'd be interested in estimating the causal effect of x on y. We'll save some of these for class, but we're going to talk about the first one here. So a classic question in labor economics: if a person gets another year of education, how much higher will their future earnings be? So we could try to estimate this in a regression where we regress earnings on years of education, which you've seen done in these slides, okay? In that regression, our y variable, of course, would be someone's earnings. Our x variable would be how many years of education did that person complete? And our regression would be telling us, for people with more education, how much higher do their earnings tend to be, okay? The unobservables here, remember, are capturing everything other than the x variable that influences the value of y for that person. This is some really important stuff in this case. The unobservables, u, would include things like intelligence, maybe the person's motivation, and maybe something like parents or other family members, like connections in the labor market that might, influence job opportunities and eventual pay levels for the person. All right, so this is an incomplete list, of course, okay, but these are some important factors that are in the error term in our regression. So let's think about how these are related to the variables. Something like intelligence. Almost certainly it's true that people who are more intelligent are more likely to get more education, and that intelligence pays off in the labor market, even if you're comparing people with the same amount of education. Okay, same idea for something like motivation. All right, people who are more highly motivated probably are more likely to like aspire to higher educational attainment. But that motivation probably also drives promotions and higher earnings in the labor market, okay? Family background, like your parents' income and connections in the labor market, right? Well, if parents are maybe high education, high income, you're more likely to get more education, which helps you in the labor market. But then you also may get a direct boost from access to professional networks or something like that, okay? So this is all this stuff right here, right, is helping to produce more earnings in the future, but also probably correlated with education, okay? These are examples of omitted variables bias. So when we're comparing, remember the beta 1 hat is just a comparison, and we run a regression and we see, oh, people with more education get paid more. Part of that is probably because they have more education, but part of it's because when you compare a college grad with a high school grad, you're comparing people who, on average, right, not every comparison would be this way, but on average, the college grads are probably going to score better on intelligence tests. They're probably going to be more motivated, persevere more, right, and have more favorable or advantageous, privileged family backgrounds, okay? And that is going to make for a case where if you were trying to understand the causal effect of education on earnings, your regression would overstate that causal effect. Okay. Are there cases where the slope estimate could be treated as a causal effect of x on y? Yeah, there are some special cases that are of interest. And for now, what I would say is the rule to keep in mind is cases where x is as good as randomly assigned. Okay, so for example, if we could design a randomized controlled trial, to my knowledge, no one's done this in the way I'm about to suggest, where we have, let's say a few thousand people would be nice to have, and we get them right at high school graduation, and we randomly assign some of them to continue with their education in college, and then some of them we say you're not allowed to go to college, you have to go get a job or something else, okay? But you can't go to college. Then we could follow up in 20 years and learn a lot about how access to college has helped the treatment group in terms of earnings or other outcomes, okay? So what we need is some random assignment of our x variable, here education, okay? Something like a lottery mechanism, or there's various types of what are called natural experiments that we might talk a little bit about later, okay? And last thing before we end here, just keep in mind this idea of random assignment of x is a different idea from the idea of random sampling, which we'll talk about later on as well. Okay, random sampling is about how our observations are selected from the population. Random assignment is how different observations come to have those different values of x, such as different values of education.